Okay, we are looking at section 3.5, exponential and logarithmic models. The 5 most common types of mathematical models involving exponential and logarithmic functions are the exponential growth, exponential decay, the Gaussian model, the logistics growth model, and logarithmic models. All right, if you would take a look at page 257, you will see the basic shapes for these on page 257. And
Are we going to need to memorize these?
I will be providing you with the formula if necessary, but as you're going to see in some of these problems, you're going to have to come up with your own model. Okay. All right. So on these, you see the pictures there, and we're going to start with number 1 on your gift. All right. For this one, it says the population P of a city is given by P equals 95,300. E raised to the 0.055 t, where t equals 0 represents 1996. According to this model, when did the population reach 150,000? Okay, at this point, you would plug in what, where?
Oh, call me. I got this. I want to get picked. I want. Give it to me. I want it. Oh, Pennsylvania?
Christian.
I want to go.
Where am I going to plug the 150,000? For P? Okay, so 150,000 goes in for P. So I've got 150,000 equals 95,300 e to the 0.055 t. Whoever's whistling,
It's not me. It's not I.
you need to cut it out, or I'm going to kick you out. I'm serious. You know, you guys laugh it up. It's Friday, last block. But this material is going to be on that test, I guarantee you, and it's going to be on the final exam. And yes, I said that on video. All right? Take it to the bank. So you better listen and understand how to do these problems. We don't have time for goofing around. On this problem, if we're going to solve this, what should we do as our next step here? Dave.
Next step. All right. The next step would probably be to divide by 95.
All right, calculators, everyone, need your help. We're dividing by 95,300. What do we get on the left side of the equation? Anna.
1.574.
1.574. At this point, what's going to be our next step in solving for T? We're trying to find out when the population is going to reach 150,000 Arya.
Would you divide by e to
We can't divide anything. If we have an unknown that's locked up in an exponent, what do we have to do? Rewrite it in log form. So Arya, what's that going to look like? Log to what base?
e
Of log to the base e of what?
1.574.
Okay, equals.
0.0552.
All right. Go ahead and get a decimal approximation for ln of 1.574. And then we're going to divide both sides by 0.055. And we're going to end up getting t equaling, or t is approximately what? Do this on your calculator. Joe, what'd you get?
Still typing. 8.248.
8.248. Do people agree with that? All right, let's take a look at number 2. What if you were not given a growth model?
Can you go back to that last? Make your own growth model.
Yeah.
So for this next one, If you're not given a growth model, let's look at number 2. You're not given a growth model here, but it says in a research experiment, a population of fruit flies is increasing according to the law of exponential growth. After 2 days, there are 125 flies. After 4 days, there are 350 flies. So how many will there be in 6 days? We know that the law of exponential growth means we are following this model here, y equals a times e raised to the bx. So I'm going to write y equals a times e to the bx. All right, let's make a little table of what we know. We know that after how many days we're going to have how many fruit flies. After 2 days, there's 125 flies. After 4 days, there's 350 flies. I'm going to be plugging in 2 for x and 125 for y in this model. So I have 125 equals a times e to the b times 2. Do people agree with that? At this point, I could solve for e, or at least get e by itself. Solve for a, get a by itself by dividing both sides by this e to the 2b. That divides out with that, and I get a is equal to 125 over e to the 2b. Notice in this equation, I still have 2 unknowns, a and b. Good thing I have 2 pieces of data to work with. So I'm going to write another equation where I'm going to plug in 4 for x and 350 for y. So I'll have 350 equals a times e to the b times 4. At this point, I can take this expression for a and substitute it in here. So I'm going to have 350 equals 125 over e to the 2b times e to the 4b. If I got e to the 4b over e to the 2b, I'm dividing 2 numbers with the same base. What do I do with the exponents? Do I add, subtract, multiply, or divide here, Vincent? Subtract. So what is e to the 4b divided by e to the 2b? It's going to be e to the what? 2b. So far I have 350 equals 125 times e to the 2b, because I subtracted my exponents. And then what do you think we're going to do next here, Carter?
You're going to divide.
Divide by 125. So if I divide both sides by 125, what's 350 divided by 125?
2.8.
Is that exact? 2.8 equals e to the 2b. And then what are we going to do to solve for b here? Mia? Okay, so what's that going to look like?
Log to the base
Of
2.8
equals 2b. Do people agree with this?
Yeah.
And you know that that's the same as ln of 2.8 equaling 2b. And we're going to divide both sides by 2. Can you give me a decimal and give me at least 4 decimal places for b? Anna?
It'd be 0.5148.
0.5148. Do people agree with that? Okay, this is great, but first of all, we're looking for A and B, and we've only found B. So at this point, we're going to take this B value that we just found, and we're going to plug it back in right here for this B, so I can solve for A. So A is going to be equal to 125 over e to the 2 times 0.5148. Can you give me a decimal for this? 44.642. Do people agree with that? All right. Now, if I plug in this A value and this B value back in my original model, remember my model is y equals A times e to the bt. So I'm going to have y equals 44.642 times e to the, what did we say it was? 0.5148 t. Does that look okay? We finally have our model written, and so now we can answer the follow-up question, and the question was, how many flies will there be in 6 days? So at this point, now that we have our model, we're going to do what to answer that, Sydney?
We're gonna plug in 6 for T.
Yeah, did I switch to T's and X, whatever, it's either T or X, whatever you want to call it, but we're going to plug in 6 there. All right, so we're going to plug in 6 right here. 44.642 times e to the 0.5148 times 6, and that gets me approximately how many flies, Eddie?
979.92.
So about 980 flies approximately. Do people agree with that? Okay, now here's my follow-up question. How many flies were there originally, like on day 0?
0.
You can't get flies from
Yeah,
0 flies.
44.
Yeah, 44. Because if I plug in 0 here, e to the 0 is 1, so there was about 44.6, about 45 flies originally. Okay.
Yeah, he's the worst.
You're number 3. Okay. At this point, let's move on. Okay, let's look at the top of page 260. So many great application problems in this section. On page 260, in living organic material, the ratio of the number of radioactive carbon isotopes, that's carbon-14, to the number of non-radioactive carbon isotopes, that's carbon-12, is about 1 to 10 to the 12th. When organic material dies, its carbon-12 content remains fixed, whereas its radioactive carbon-14 begins to decay with a half-life of about 5,700 years. To estimate the age of dead organic material, scientists use the following formula, which denotes the ratio of carbon-14 to carbon-12 present at any time t in years. So we are going to be using this formula that says the ratio is equal to 1 over 10 to the 12th times e to the negative t over 8,223. All right, so for this problem, if we want to find the age of this fossil where the ratio of carbon-14 to carbon-12 was 1 over 10 to the 14th, we're going to plug that in. We're plugging that in for the R. And then what do you think we're going to do to solve this equation? What should we do first here, Hannah Taylor? Divide by, we're already divided by 10. Should we multiply? Yeah, let's multiply both sides by 10 to the 12th. 12. So here, this 10 to the 12th divides out with this one, and if I've got 10 to the 12th over 10 to the 14th, that's going to end up being what? I am dividing two numbers with the same base, so what do I do with the exponents? Subtract. I have to subtract, so I'd get 10 to the negative 2, wouldn't I? Equals e to the negative t over 8,223.
Ms. Presley,
Yes, Ed?
do you care if you keep it as 1 over 10 to the second?
That's fine. You can write as 1 over 10 to the second. You could even write as 1 over 100. You could write as 0.01. Either way, this is a real life problem. We're going to get a decimal kind of answer. So I have this, and then what are we going to do to solve for t in this situation? Vincent?
You're going to put it in log form.
All right, so what's that going to look like?
It's going to be log base e of 1 over 100
All right, equals negative t over 8,223. And so at this point, this is ln of 1 over 100 or ln of 0.01. And you could maybe multiply both sides then by, like a negative 8,223. Right, take this and multiply by negative 8,223. Won't that get rid of the negative and get rid of the 8,223? Is that okay? I'm multiplying both sides. I took this and I multiplied both sides by 8,000. It's kind of smashed over here. I'm multiplying both sides by negative 8,223, right? Negative times a negative is positive. Those are dividing out. So I get T is approximately equal to what? How many years old is this fossil? Zach?
37,868.3.
All right, so 37,869 maybe if we round to the nearest year? Yes? 68.
I got.
All right. Are we okay with this? That's the number of years old the fossil is. Eddie?
Oh, I got 85. 37,885.
Okay, so roughly the same.
Is that okay?
Yeah, I think you want to be keeping as many decimal places like stored in your calculator as
Well,
possible.
I did the ln of 100, 1/100.
That's fine.
So is it okay if I already got the answer for you?
I mean, as long as you're showing all your work, but I would say keep as many decimal places as possible. Okay, let's move on. Okay, so that brings up this example. The value of B in the exponential decay model, here's our exponential decay model. The only difference between this and the exponential growth is what? There's a negative in front of the B, okay? And that is going to determine the decay of a radioactive isotope. So I was going to do this extra example, but because of time, we'll just get right to the one on the gift. Eddie?
We have to memorize this formula.
No, I will say use this exponential decay model or this exponential growth. But like the fruit fly problem, you got to make up your own model, right? You got to find your
You're
own.
giving us that formula.
Okay, Joe, did that answer your question? Okay, so at this point, we're using y equals a times e to the negative bt, right? Let's talk about what these things are going to mean in a half-life problem like this. All right, so this a right here is the initial amount. Okay, this y right here is the amount remaining after t years. Okay, t obviously is going to be the number of years, and this b value is just a constant that holds for the life of this problem, and then when you do another problem, you get a new b value, and so on, right? That's just the constant. So, in this case, let's make a little chart for the amount remaining, and, no, back it up. Let's go with year and the amount remaining. So if I start at year 0, and let's just make up an amount like 100 grams. So I'll come back to this problem in just a minute. But if I have 100 grams in year 0, and the half-life is 24,100, then after 24,100 years, I should have how many grams remaining? Zach? This is not a calculator question, this is just a thinking question, and do you understand half-life? So after the half-life number of years, we should be down to half of what we started with.
Oh, so like half of what?
We started with 100, so we should be down to what?
50.
50. So after 24,100 years, we're down to 50 grams. What if we go another 24,100 years into the future? That would be 48,200 years. Then how many grams should be remaining here? Kathleen? 25, right? Every 24,100 years, you're going to lose half of what you had before. Will we ever be down to 0 grams? No. Will there ever be no plutonium or whatever it was left in Chernobyl? No. It's never going to be down to 0.
Why
Okay.
is that?
Because you keep just taking half. You keep taking half, you're never going to get to actually 0, right? You're going to get to some decimal answers or fractions.
Right, but when you keep going, like with those decimals, and it just keeps getting smaller. Like,
Right, but it's always going to be positive. Never going to actually get to 0, right? You'll get half of a half is a fourth. Half of a fourth is an eighth. Half of an eighth is a 16th. Half of a 16th is a 32nd, and so on. You're never going to get to 0. Okay, so for this problem, we don't know this constant, right? But they're saying in 1,000 years, there's going to be 2.1 grams remaining. Guess what? We're not ready to plug in 1,000 anywhere or 2.1 anywhere. We must find this constant first. And the only way to find the constant first is to use the idea that in the half-life is 24,100. So let's make up, here's my model, A, B, negative BT. Let's make up an initial amount. Let's just say 100 grams, like we were saying. E to the negative BT. And if I plug in the half-life number of years of 24,100, then how much will be remaining? If the initial amount was 100 grams, after 24,100 years, how much is going to be the amount remaining? 50. So I'm going to plug 50 in right here. Does everybody understand that?
I don't understand.
Eddie?
Because in the question, it says after 1,000 years, there's only.
We'll come back to that question.
Just
We've
make
got to
up
find,
numbers?
yes, we're going to find a constant first. But Eddie, everybody in this room could come up with a different amount for the initial, like you could pick 20, and over here you'd put 10.
We're getting the
And
same
if Kathleen
answer?
says, I want 40 grams originally, then she's going to have 20 grams left after this many years. But the point is, when all of you make this division of whatever it was, you're all going to be left with what over here? 1/2. So I'm going to write 0.5 equaling e to the negative 24,100b. I just rearranged those. At this point,
It's hilarious.
at this point, we're going to rewrite this in log form. So we're going to have ln of 0.5 equaling negative 24,100b. All right? Everybody okay with solving for b?
Divide it, yes.
All right, let's divide both sides by negative 24,100. Calculators, please, and can you give me, let's say, 6 decimal places for b? Anna?
It's negative 0 point, and then you have 4 zeros, 29.
Okay, but the b value itself is positive, right?
Yeah.
So 0.00029
Yes.
is my b value. Does everybody agree with that?
Yes.
Okay, but remember, our formula does have a negative in front of the b, so that means my model should be y equals a times e to the negative 0.000029t. Does everybody agree that that's our
Wouldn't it be a
model?
positive 0.2 or 0.00?
The b value is
Well,
positive,
no, because
but we got a negative in the formula. So we're just going to put that negative in front of our positive. All right, at this point, slide this over here.
How'd you get positive?
So now,
Because ln of 0.5 turns out to be a negative number, and I'm dividing by a negative number, right? And so that b value turns out to be positive, but there's a negative in the formula. At this point, now that we have the constant, now we're ready to answer the question, which was, after 1,000 years, there's 2.1 grams remaining, so what was the initial quantity? So where am I going to plug in the 1,000? 1,000 years, so that's going in for t. And it says that after 1,000 years, there was 2.1 grams remaining. So where does the 2.1 go, Trent? The A, do people agree?
it's Y.
The Y is the amount remaining. The A is the initial amount,
Okay.
right? So the 2.1 is going to go in for the amount remaining, correct?
Yeah.
So we're going to have 2.1 equaling A times E to the negative 0.000029 times 1,000. Are we okay with this? All right, Brendan.
I was going to take it to the next step.
Go ahead.
If you want to. So you could make the exponent into negative 0.29.
Because we're sliding this over 3 spots.
Yep.
So E to the negative 0.029.
And then we can rewrite that in logarithm form. Or no, actually no, we want to divide by a.
Well, let's keep it, we're trying to solve for A, let's keep A there.
Okay, divide by E, actually.
Divide by E to the negative 0.029. So that divides out with that, and we get A equaling what? Give me like 3 decimal places.
162. Round up, you round up.
2.16,
179.
we're arguing about this. What is it, 2.162?
Yeah.
Something like that?
And what did you?
Okay,
That looks
now,
right.
listen, it's not much higher than the amount remaining, which was what, 2.1? It's a little bit higher, and that makes sense because we only went 1,000 years into the future. So we started with this many grams. This is the initial amount. And then after 1,000 years, it's only down to 2.1 grams. But remember, the half-life is 24,000 years, right? So I think this answer seems reasonable. Let's take a look at what else is on this gift. Gaussian models, I'm going to skip this one for right now. But I do want to look at logistic growth models. Now, with logistic growth models, let me slide this down. I mean, this is the general model like this, but if you look at a graph of these, the graph has 2 horizontal asymptotes because the shape of the graph looks something like this.
Wow.
Okay? This logistics graph is perfect for this type of situation. On a college campus of 7,500 students, one student returns from vacation with a contagious and long-lasting flu virus. The spread of the virus is modeled by that Gaussian model, where t is greater than or equal to 0, and y is the total number of students affected after t days. The college will cancel classes when 30% or more of the students are infected. How can we find out how many students will be infected after 4 days? What should we do here, Trent?
Whoops. I'll silence this.
Please. Trent, how are we going to find out how many are still around or how many are infected?
What should you do? Put in 4?
For what?
For T?
Sure. Gabe, put that away.
Silence me.
Thank you, sir. And so we're plugging in 4 for T. So we have y equals 7,500 over 1 plus 7,499 e to the negative 0.9 times 4. Calculators, please. How many people are infected after 4 days? Sammy, what'd you get?
36.4 people.
Do people agree? 36.4? Okay, so we'll say 36.4 students. And we could round just to 36. But then it says, after how many days will the college cancel classes? Well, they're going to cancel when 30% of the 7,500 students are infected. So what is 30% of 7,500? Anna? 2,250. 2,250. So how am I going to find out how many days it's going to take for the college to cancel classes? Oh, look, back up for a second. Remember, the reason why this graph is perfect for this model is because, yes, the number of cases of this flu is going to rise, but it is going to eventually level off to the total student population, right? Pretty soon the whole school would be infected if nothing happens, but it's certainly not going to get any higher than 7,500. Does that make sense? That's why it's leveling off. Okay, so for this case, where are we putting this 2,250 in this model? Sam?
For y.
Y. So we're going to plug in 2,250 equals 7,500 over 1 plus 7,499 e to the negative 0.9 t. Did I do that right? Look okay? Talk me through solving this. Anna, what should I do first?
I would multiply both sides by the 1 plus, like by the denominator.
Yeah, let's multiply both sides by the 1 plus 7,499 e to the negative 0.9t. All right, so in this case, this is gone, this is gone. I've got 7,500 on the right, equaling 2,250 times 1 plus 7,499 e to the negative 0.9t here. What should be our next step here, Madeline?
Divide by 2250.
All right, let's do that. Dividing both sides by 2250. And so in this case, that's gone. I've got 1 plus 7,499 e to the negative 0.9t. And what does this turn out to be?
3.33.
3.3, repeating? Can people agree with that? All right, I'll just list it as 3.333. And then what would be our next step in solving for t, Sammy?
You can subtract the 1 over.
All right, subtracting 1, I've got 7,499 e to the negative 0.9t equaling 2.333. Then what are we going to do next here, Dan Martin?
Put it in log form.
One step first.
Well, I'll divide by 7,499.
Okay, dividing both sides by 7,499. And so we end up getting e to the negative 0.9t equaling, can you give me a decimal for this? How many zeros?
3,
3 zeros, and then what?
311.
311? Okay. Yes?
00311.
Okay, and so at this point now we'll rewrite it in log form, right? So we'll write log to the base e, or you could just write ln of what? 0.000311 equaling negative 0.9t. Do we agree with that?
Yes.
All right, and at this point we can divide both sides by negative 0.9. And we get t is about how many days until they end up having to cancel all classes, Eddie?
8.97.
About 9 days? 8.97. So about 9 days until the college has to cancel classes. Are we okay with this? Wow. Okay, so far any of these problems could be on your test, and some of them will be on your final exam. Okay, let's see what else we can talk about from this. Have you heard of earthquakes with the Richter scale? Okay, so Richter scale rating, the magnitude R of an earthquake of intensity I is given by this formula, R equals log of I divided by I sub 0. I represents the measure of wave energy, and I sub 0 is the minimum intensity used for comparison, and we're just going to plug in 1 for that I sub 0. Okay, I sub 0, we're just going to use 1. So let's see, is this one of the questions on your gift?
No, it's a different one.
Is this it?
Yeah.
Okay, it says find the magnitude R of an earthquake of the given intensity. So using R equals log I over I sub 0, but remember we're just going to plug in 1 for I sub 0. Okay, and we're going to plug in 68,400,000 here. And so the Richter scale rating would just be the log of 68,400,000. And what does that turn out to be? By the way, that's base 10 then, right?
7.
Eddie?
7.8.
All right, so about 7.8 on the Richter scale for that one. Okay, let's go back to this example though, because I think this is another interesting one. If I tell you the Richter scale rating is 9, can we find the intensity? So then I would say 9 equals log I, and then what would I do to find the intensity? Anna?
Put it in exponential form.
And what's that
So
going to look
you
like?
have 10 to the 9 equals I.
All right, 10 to the 9th equals I, and 10 to the 9th would be a 1 followed by 9 zeros, right? So that would actually be, what, 1 billion? Right? 1 billion compared to this example where it was only 68, well, I guess that was 68 million, right? So 1 billion, obviously a lot bigger than 68 million, and the Richter scale only went from 7.8 to 9. So the Richter scale is a logarithmic scale, right? So in other words, an earthquake that has a magnitude 7 is going to be 10 times as powerful as one that's a magnitude 6. So every time you go up 1 on the Richter scale, you're going up by a magnitude of 10. So a magnitude 7 earthquake and a magnitude 9 earthquake, the magnitude 9 is how many times bigger than a 7? 100. 100 times as severe. Okay. Brendan?
Are you gonna need to know how to do these both ways?
Both ways.
Can you go back?
You should know how to do both ways.
Gotta take a.
So if I either give you a Richter scale rating, like in this example, where we plugged in 9 for R, and you had to rewrite it in exponential form to get the intensity, or I give you the intensity, and you need to find the Richter scale rating. Right? You should be able to go both directions. Can you go back down to the, go back to the previous page?
Yeah.
Back here?
Can I take a picture of that one?
You can. All right, what else is on here?
So we skipped number 5.
Skip 5 though.
We skipped number 5, but we got through everything else?
Yes.
All right, so, nothing else? Okay, yeah, and let's not worry about number 5. But,
So what's that?
So just chill.
yeah, 5. 5 not bad.
I think
Okay.
I'm caught up today.
So, your homework is on Blackboard.
Good job, Dan. Way to listen to this one.